F324 June 2012. Question 1. This first question is a benzene question. It's a lovely, lovely question. In this first part A, what we're really looking for here, a few things. So we've got alkenes and benzene both react with bromine. It's a fairly standard question. Explain the relative resistance to bromination of benzene compared with alkenes. And the bit I want to highlight here is perhaps not the most important word, but compared with alkenes. You've got to make sure that this question is all about comparison. So to start with, we want to say exactly what there is in both cases. So let's just get my font right. To start with, we can say that benzene, thinking about the structure of benzene, it wants to know about these electrons, where they are and the type of bonds they're formed. So we've got benzene has a ring of, well, let's have a pi ring, shall we, to be even more precise, a pi ring of delocalized electrons. Notice here, I want to be spelling delocalized correctly, because it says you should use appropriate technical terms spelled correctly. So the fact that I've got delocalized electrons, my technical term, I must spell it correctly. I'm just checking because it's got a red line underneath. I think it is spelled correctly. Then, all importantly, you've said what benzene's got. Compare it to alkenes. And to do that, you've got to actually say what the alkenes have got. So, alkenes have, what do alkenes have? A pi bond between two carbons. And it's important to say what's going on with the electrons as well. The electrons, where are they? The electrons are not delocalized this time, but localized in the bond. So we've covered 2 marks there. We've said what benzene is like, where its electrons are, and we've said what alkenes are like and where their electrons are. Now we've got to pick up 2 more marks, 4 marks worth for here. So what we need to say next is, yeah, the electron density, isn't it? So the electron density, can't seem to be able to spell at the moment. The electron density is higher in alkenes, lower in benzene. The electron density is lower in benzene. What does that mean then for the attacking electrophile? What can we say about that? Generally, we've got benzene doesn't polarize that electrophile as much, and it's another key word, polarize. You could also use the word attracts, so benzene attracts bromine less, or benzene induces a weaker dipole. But I think we can go with here. Benzene polarizes bromine less. And there you have your 4 marks. they've given you a lot of space to write, but essentially it's just 4 very key points. Benzene has a pi ring of delocalized electrons. Alkenes have a pi bond, and the electrons are localized. And the electron density, therefore, in benzene is lower. And just thinking about that, in the pi ring, you've got 6 electrons delocalized over 6 carbons, where in the pi bond, you actually have a sigma bond and your pi bond, don't you? Where you've got 2 pairs of electrons, so you've got 4 electrons between 2 carbons. Whereas in benzene, because you have that ring, you have less electrons between each carbon. And so benzene polarizes bromine less. Okay, in the second part of this question, we've got 2 reactions with phenyl ethene, which I've drawn out terribly there for you, but I think you get the rough idea. You've got a bromine attached to ethene essentially. So in the first reaction that we're looking at, it's just phenylethene is just mixed with bromine at room temperature, and you've got a molecular formula of C8H8Br2. So in this case, all we're going to have is that our C8H8Br2, well, just looking at this, we've already got 6 8Cs. We've got 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. All I need to do is add 2 bromines on. It's at room temperature, so it's going to react with the alkene part, and I'm just going to lose that double bond, and I'm going to get 2 bromines there. So my structure, hopefully I'll be able to draw it reasonably. Here we go. See, 1 single bond now with a bromine up top. Yeah, as you can see, I can't see my cursor, so I'm just sort of guessing where I'm drawing these now. And down to the benzene ring, which is going to be a little bit tricky here. And so I get my structure, which might just get me 1 mark, if you could actually understand what I've drawn. But there you are, for 1 mark, there's your structure, and it matches the compound, the molecular formula that we've got, which I can't point to because I lost my cursor. So, hold on a second. B2 then asks you to predict the number of peaks in carbon-13 NMR following reaction 1. And so, counting round, where should we start? Here. 1 individual. It's not in nothing, no carbon in the same environment as this. 2, 3. I should perhaps try and number these, shouldn't I? Here we go. Let's see if my cursor will work here. So we've got 1, 2, 3. Now these 2 are in the same environment, so they're both 4 because they're connected to exactly the same thing, being 3 and 5, which are both in the same environment. And then finally we have 6. So the answer to this question is 6. Now, part 3 of this question, which is over the page, is going to focus on reaction 2, where the student has added a halogen carrier to the mixture obtained from reaction 1. So we're now adding a halogen carrier to this molecule, and we're getting a mixture of isomers with a molecular formula CH7Br3. So from here we can see we've lost a hydrogen and we've gained a bromine. And if you're hot on your benzene topic, which you should well be, you'll realize that instead this time of reacting with the alkene, we've got here a substitution occurring on the benzene ring. We've got isomers forming, and as we have got something at position number 1, we can see that our bromine can be substituted on at different positions around the ring and give us different isomers. So going over the page, we've just got to draw two structures of these, and let's see if my luck will hold. Trying to draw some of these out. So we've got the same situation as before at the top. Down here we've got my benzene ring, and I've got bromine here on position 3, and if I do the same again, should have done this, should have had one ready prepared. Just check that I'm not missing anything out. Make sure you always draw fully your H's. And on this one, just to keep my bromine away from the rest of the molecule, so it doesn't get mixed up with that H there, I've put it down there. You could have it there, there, or there, so I've chosen 2. To finish this question then, you have to state the types of mechanism that's occurred in reaction 1 and 2. So if reaction 1 was with the alkene, and so you have, I won't, oh, I've lost my cursor again. Hang on a second, where's it? Oh, I know what I've done. Oh, look at this. Right. Let's put it in. So, we've got, first of all, with the alkene, it's got to be an electrophile because it's got the attacking species has to love electrons, and both benzene and the alkene are electron rich. So it's, for both cases, it's electrophilic. And I'm just going to check my spelling of electrophilic. Remember how many L's? It's just the one L there. Electrophilic, in this case, because it was the alkene, I'm adding across the double bond, so addition. And for reaction 2, electrophilic. And this time, the bromine on the benzene ring is substituting the hydrogen. So substitution. Just as we finish, just remind me what is the definition for an electrophile, and we'll pick that up before we begin question 2.